All right, now we're going to do a full problem where it says find everything. And look at this thing. It's not as bad as the last one as far as setup goes, but you know, it's weird because you can't say that current is constant because current is constant and then it splits up down these paths and it gets back together. You can't say voltage is constant because it drops here, then it's constant here, and then it drops again. So we're going to have to do some crazy stuff. But the good news is, what we learned in the last notes video is I can take this crazy thing and I can simplify it down in order to find total resistance and total current. So right now it looks like a series here and here, but it looks like a parallel there. So I'm going to take this guy and simplify him down. So I'm going to do 1 over resistor 2 comma 3 equals 1 over 4 ohms plus 1 over 12 ohms. Okay, so when I do the whole 1 over thing, and I can show you that, I can do 1 over 4 plus 1 over 12 equals, and then I use my -1 button to flip it. So we get 3 ohms. All right, so those two guys together are equivalent to a single 3 ohm resistor. So I'm going to redraw my picture, right? I have a 24 volt battery, then it goes through a 5 ohm resistor, then it goes through a 3 ohm equivalent resistor, and then it goes through an 8 ohm resistor. So this is R4, this is equivalent to R2 and 3, and this is R1. So we got it a little more simplified, right? We took care of that one. And then we can take it even a step further and combine this one, this one, and this one. Now that they're all in series, they kind of add up. So we can draw the most simplified version, which is just a single resistor 1 through 4, and what it's equivalent to, also known as your total resistance. So we still have our 24 volt battery, and if I put all these together, you got 5 plus 3 plus 8 is going to be 16 ohms. Okay, you can either write that, sometimes you'll see people write this, REQ, because EQ is for equivalent. It's equivalent to a total resistance of 16. So I already know one of my answers. I already know total resistance, 16 ohms. Once you know total resistance, you can get total current, because we just have to use good old Ohm's law, right? And cover up current, you get V over R. So, so I'm going to keep my work kind of organized, and I'd like you to do the same. So we're going to find our total. Here's my picture section. I'm going to block that off, right? We'll come back to those in a while. But finding IT, you're going to say IT equals VT over RT. Ohm's law, VT is 24 volts. RT is 16 ohms, and 24 divided by 16 is going to leave you with 1.5 amps. Now I don't need to move that decimal place because it's a number between 1 and 999, which is kind of nice. I don't have to do all that unit conversion stuff. Awesome. Okay, now here's what's crazy is we need to find the current at each spot and the voltage at each spot. Well, the good news is, remember, in series, current is constant, right? That was one of the first things we learned. In series, current is constant. So you can go back to the beginning picture. Don't go to the later ones. But if you go back to the beginning picture, any resistor that was in series and not parallel, so I circled the parallel part, right? But these guys were in series with my resistor. There's only one way for the electricity to flow. Here, there's only one way the electricity to flow through here. If they are series parts, I get to say that the current is constant. So your total current is going to equal your current at resistor 1 and your current at resistor 4. That makes sense. Since they're in series, I'm allowed to say the current flows through them and them alone. It doesn't get to branch off like it would here. So it has to have your total current. It doesn't just go away. So I already know that my total current on those is going to be 1.5 and down here 1.5. Now my other two, that it splits up. It splits up down the branches. So we'll deal with that later. Okay. I can also deal with the voltage drop on these two guys. I can't deal with the voltage drop here yet, but I can on these two because if I know the current on resistor 1 over here, we just found it, and I know the resistance on resistor 1, guess what I can find out? The voltage drop on resistor 1. So you got 24 volts coming in. How much drops off here? So we're going to find voltage drop on R1 and R4 since we know their currents. Okay, so we're going to find our voltage drop on R1 and R4. So V1 equals, all right, cover up V, right? I times R. I1 times R1. So in this problem, that's going to be, what's my I1? I1 is 1.5 amps, and R1 is 5 ohms. Okay, for a grand total of 1.5 times 5 is 7.5. And what are my units? Amps times ohms leaves you with volts. So I got that. Okay, so 7.5 volts have dropped off by the time I passed over that. Now I don't know here, we're going to have to deal with that in a second, but I do know the current at 4 and the resistance at 4, so I can do the voltage drop at 4 very similarly. V4 equals I4 times R4, and that's going to be 1.5 amps, and we have a resistance of 8 ohms at resistor 4. So these aren't that hard. It's just, it's possible to get confused and not know the order to do things in. I kind of let the problem flow, like I knew I had to start with RT, and then I knew I could get that, and then I used my series rule to get these two, which forced me to get the voltage that goes with them because of Ohm's law. Now, here's what's kind of cool. I used this fun little fact here, right? In series, current is constant. What I haven't used yet will unlock the rest of the problem. Because, what haven't I used yet? In series, current is constant. In parallel, what is constant? Voltage is constant. Well, how does that help me? Remember PVC? And parallel voltage is constant? Well, what that means is I know my current breaks up over these two branches, but it's like a stairwell. They both go down the same amount. So the voltage drop here has to be the same on R2 and R3. So good old subtraction is going to be our friend. You can do this two ways. One, you could say, I know that their total resistance is 3 and their total voltage is 24. Or you can use your noggin and say, wait a second. If my total ohms are 16, or sorry, my total volts are 24, and I've used up 12 of them here, and I used up 7.5 of them here, right? I used 7.5 drop in here, I used 12 of them drop in here. How many volts are left to drop here? Because they have to drop. You're going down two different stairwells, but you still have to drop the same amount. So I don't know why I did that. But I can take away the other, and I know these are 4.5 volts. I could have also done, I could have also used this guy here. And I could have said, okay, the voltage drop at 2,3 equals the resistance, or the current at 2,3, which is 1.5 amps, because it's behaving like a series, times the resistance at 2, 3, right? And guess what you get when you do 1.5 times 3? Same answer. So I don't care how you do it. You could use this guy in Ohm's law, because it's the series equivalent of this, or you can use your noggin and say 24 volts, I dropped 7.5, I dropped 12, so all that's left is 4.5, and since they're in parallel, they're both 4.5. So to summarize down here, voltage total minus voltage at 1 minus voltage at, voltage at 4 will equal voltage at 2 and 3. So 12 minus 7.5, 24. 24 volts minus 7.5 volts minus 12 volts equals the voltage at 2, 3. So this looks terrible because my writing was bad, but the total is 4.5 volts on both of them. But now it leaves us with our last thing, and that's if I know V2 and I know R2, I can find I2 with Ohm's law. I can do the same with these. So now we're going to find how much current goes down each branch. Okay, so we're going to find I2. So we cover up I, we say V over R. So I2 equals V2 over R2. And V2 is 4.5. We just found that, right? 4.5 volts. R2, back to our original picture, was 4 ohms. So I2 is going to be whatever 4.5 divided by 4 is, and that's 1.125 amps. Okay. And finally, we're going to find, let me write that up here, 1.125 amps. So it's kind of like the problem leads you down the path. I didn't really decide what I was going to do first other than my total resistance and total current. And I kind of let the problem flow. All right, I3 equals V3 over R3, good old Ohm's law. Voltage is still 4.5 volts. Oh, geez. And my current, or sorry, my resistor on there is 12 ohms. So if I take 4.5 divided by 12, I get 0.375. Ooh, we finally have to convert one. So move, move, move. 375 milliamps. Because I'm going to use that as my answer. I don't want to use a decimal. So 375 milliamps. Guess what you would get if you added the 0.375 and the 1.125? You would get your total current of 1.5. So what that's telling you is the current's 1.5 amps through here, but when it gets here, it branches off, and most of the current goes down this path, and a little less current goes down that path, because it has more resistance, so who would want to go down the slow road, right? But man, look at that beauty. Isn't that nice? So now you can go back to your problems. Hopefully you simplified them all down and found RT from before, or R equivalent, on your crazy ones on your worksheet. And now you can go through and calculate the rest of the stuff. All right, good luck to you, and I hope you do awesome. You can always send me questions if you have them. Later, people.